Okay, welcome back. This is the video for the fourth problem on Superquiz 1. So here, this is given as a bit of a word problem, but we have to read through and find the math. So first, they're telling us there's a useful differential equation for forensics, and the differential equation we can see is on this line in the middle. And so automatically I see there's this k and a y naught, which the next line tells us, right, are experimentally determined constants. So that means they're just given to you by some sort of an experiment. So the variables in this equation are going to be the y and the t. All right? Cool. What do they want us to do? Well, it says we need to use the fact that this is a separable differential equation. Oh, how nice. So it's going to be separable to find a general solution. Okay, so since it's a separable differential equation, well, remember there's a two-step process here. We want to separate and then antidifferentiate. So to separate, I want to put all of the y's on one side and all the t's on the other side. So let me copy the equation again. And recall, okay, k is a constant, so I can do anything I like with it. Same with y naught. That's also a constant. So how about we multiply both sides by dt, so that'll move it to the right, and we can divide by y minus y naught. All right? I can't divide by just y because there's this difference here. But I can divide by this entire difference because it's multiplied by the k. So I'll divide by y minus y naught. So when I do that, I'll get dy divided by y minus y naught equals k times dt. Okay, so then as we know, once we separate, we're going to antidifferentiate. So I'll antidifferentiate both sides, and the rule is when you have an equality, as we did over on the left, and you antidifferentiate both sides, you have to add a constant of integration. Right? Otherwise, the equality will generally not be true. Okay, now the right-hand side antiderivative should be pretty easy. This is k is a constant. I could even pull it out of the integral if I like. And I would get kt plus c. And on the left-hand side, well, boy, I really wish this was y instead of y minus y naught. Then I know just ln of the absolute value of y. But as we've seen before, we're just going to guess that the y minus y naught is no different. And if we took a derivative, we would get 1 over y minus y naught times the derivative of y minus y naught, which is just 1, because, well, there's just a 1 coefficient in front of the y, and the y naught is a constant. All right, so if I want to try to isolate this y, I could now exponentiate both sides. And if I did, I would get absolute value of y minus y naught equals e to the kt plus c. And we've seen in the past when we have this form, a to the kt plus c, we break it up as e to the kt and then e to the c. And this e to the c is going to be a constant, which we could call something like d. And now I have this absolute value that I don't really want to deal with, and so I know that taking the absolute value just turns positives to, well, actually keeps them positives, or negatives to negatives. So it just changes the sign, and I can just let the sign be absorbed by this d. So I could actually just drop the absolute values and realize the d is going to handle all the sign issues. And then I can add y naught to both sides. So this will add y naught, and we'll have y equals y naught plus de to the kt. And so we found a general solution. Again, we could check it by taking the derivative with respect to t, and if we did, we'd find you'd got k times y minus y naught.